All right, folks, welcome to the first question on the backtracking pattern that we're evaluating. Uh, Now, a lot of these solutions will have a recursive slant to them. However, and which means they will be medium to hard, right? And this one is a hard problem according to LeetCode, and you're gonna see why. Also, worth noting, um, recursion is not exactly a safe path for writing code. Now, it's many times it's an elegant path, but not always safe. I saw this video about how NASA writes code, and they always favor an iterative solutions to recursive solutions, just because recursive solutions are hard to debug. And if you follow these videos and you see me debug JavaScript in the past, you would notice how for every call to a function, you cannot inspect the previous call to that function. And so by default, that's the mechanism for recursion is a function calling itself. So you lose that context of the previous call, whereas in a while loop or in a for loop, you still have like complete insight into better insight into what has been happening. So they tend to be easier to debug. You can put breakpoints and have them be more useful to you, basically. So let's get into it. It's probably going to be a long video. N queens. So we have a chessboard of size n by n, and we want to determine how many ways n queens can be placed on the board such that no two queens attack each other. Now, if you know the game of chess, you know that a queen can move horizontally, vertically, diagonally on a chessboard. One queen can be attacked by another queen if both share the same row, column, or diagonal. And these are the constraints. So n is less than or equal to 9. So we can't have more than 10 rows or 10 versus 10 columns in the grid. So here it is. Here's an example. N of 4. There are two different ways to arrange 4 queens in an n by n chessboard, such that they don't attack each other. You can see that here. This can be attacked anyway, horizontally or vertically, or diagonally, and the like. Okay, so there are 2 different ways. And for 6, we see that there are 4 different ways. So how would we go about solving this in code? Let's find out. For the solution to this problem, I mean, there's a naive solution where you find all configurations with all possible placements of n queens and then determine for every configuration if it is valid or not. So you're checking every single way this could happen. And this is the time complexity, right? Exponential. Is that exponential? N squared. That's a weird notation. I'm not sure what that is, but this is a big number. Okay, so very expensive. Bad. Don't do that. The brute force approach is essentially like O of n to the power n, right? Or n to the power, yeah, O of n to the power n. I don't know why they represent it like this way, but that is huge. And so our optimized solution is going to use backtracking. And we've seen backtracking in the subset pattern, the series of videos under the subset pattern for quite a number of problems. And now let's look at the problem. I highlighted some things here. Once we place the first queen anywhere in the first row, no other queen may be placed in that row, which is true because the queen can eat anything on the same row with it or the same column with it. Therefore, the search for a safe position for the next queen starts from the next row. And this gives us a simple means to store a solution. We simply need to store the column of each row. That is a list of n column indices, each representing a safe placement. So when we're storing our solution, we don't need to store, we can rely on the index for our solution as the row and just keep track of just the columns, because we know that there's only one queen per row. And as there are n rows in a given board, and each row may safely hold just one queen, in any valid solution, all n rows will be used, right? So n queens in an n by n board, all n rows will be used because no two queens can share any individual row. No two queens can share any one individual row. So with that knowledge, we can check the validity of a solution as well as and check whether a solution is complete. Because if it's at the last row, the the solution is complete. So there are two solutions to this. They give a recursive and an iterative solution. I'll go in depth into the recursive one, and I will touch on the iterative one just a little bit. So to solve the n-queens problems, similar to depth first search of a tree, two conditions that cause us to backtrack, but for two different purposes. When we find that we cannot place the current queen in a particular row, that's one condition. When we see, oh, you can't place the current queen in a particular row, so we have to backtrack and alter the position of the queen whose position was decided before. That's the prior queen. Next, we move forward again to find a safe position for the current queen. Okay, that's one instance where we have to backtrack when, oh, the current queen doesn't fit in any column in the given row. Okay, so we have to backtrack to the one we said before and change that. Otherwise, we found a valid solution, and we need to find all the other valid solutions. So we made it to the end, in this case, for example, and we just have to backtrack by removing the last screen and resuming our search for solutions from that point. So in order to find all possible solutions, we need to backtrack row by row all the way back to the first queen placed on the board, changing its position, and then looking for alternative solutions. So let's run an example for a 4x4 board with 4 queens. The bottom row first, we consider that bottom row first, and the leftmost column as the first column, so the corner down here. And then second row, we can place the second queen in the first two columns. We can't place it here because it's going to eat. We can't place it here because it's going to eat diagonally, but we can place it here. Nice. In the third row, there's no column where we can begin to place the third queen. So there's nowhere. For the next row, we realize that we can't place here, we can't place here, we can't place here, we can't place here. That's a problem. So we need to backtrack. So we backtrack. Oh, we've tried these 3. Next, we're going to try this. That's the 4th column. Okay. Now we can put something here because nothing can eat it there. However, we cannot put anything anywhere here because this is going to cover all these and this is going to cover this. So we need to backtrack again. And because there's nowhere else to go here, we come back to the first thing and move that to the next column. And then we try again. We do it again. We know that nothing here can work. We put it here, row by row. This is going to work. And next, this is going to work. And we found one solution. We found one solution. We're at the edge here. We need to backtrack again and try this next thing, and so on till we get to the end of our solution. So we're going to look at it step by step, and you want to pay close attention because we're going to construct the solution. This is one of the first times I'm using this there, construct the solution approach to explain, and it's because it's more complex than a lot of other things we've covered so far. So the algorithm goes through these steps. Place a queen in the first column of the first row. Place a queen in the first such column of the second row where the placement is permissible. Okay. If no column is found, backtrack to the previous row. Try it again in the next column. Continue to reach your last column. When you reach the end, you found one valid solution. After that, you backtrack and try another column, etc., etc. So we're going to have a results array that will store all possible solutions, a solution array to keep track of the current solution. We have is valid move that checks whether the desired move can place a queen in a safe position. The move is valid if a queen is not vulnerable to attack. Okay. All right. So they highlighted some things for us. This is a utility function that prints the board. And this is the is valid move, the thing that checks if something is valid. So we send a proposed row, a proposed column, and our current batch of solutions. And before I come to what they've highlighted, let me show what it is we're doing, basically. So this is the function that's going to solve what we're looking for. And we're just going to have a test, right? So this is a sample solution. We've seen 0 and 2, and we've not set the 3rd and 4th column. Now these are just hard-coded values. They're not, in this case, n is 4, essentially. So we're saying that in theory, if you have 0 and 2 here, and you haven't set these two, what happens. And we have a series of moves. This is the row 2, so I have 0th index, so 0, 1, 2. And these are the different columns, just as a thought experiment. So we're checking if it's a valid move. This is a call to is valid move. And let's run this and see. Lots of console logs everywhere. And so there's a main down here. So queens 4, chessboard is 4x4. That's what this does over here. And we're gonna call solve n queens for this solution. And within solve n queens, we start saying we're initializing the variables, as you can see here. We have the results, the solutions, as you can see, logged down here, and the intermediate solution. And now we get to the moves. These are just moves that we hard-coded that try every single column in the third row. Every single column in the third row. So for each one, check if it's valid. We're passing in the row, the column, so 2 and 0, and the current solution, which we have up here. And now we can look at what happens in there. So we have a proposed row, a proposed column, proposed row of 2, proposed column of 0, if you remember down here, 2 and 0. And up next, you can ignore most of these. Like we're just using this for formatting so that they're indented properly. And you can forget this call. That's what prints this, basically. So we have the proposed row 2, proposed column 0. So that's here. As you can see, 0, 1, 2. This is what we're checking. And now we keep track. We loop through everything up into the proposed row because the queens are built from bottom up. So that's what's going on here. The old row of I, the old column solution indexed at I. The diagonal offset is the proposed row minus the old row. So in this case, the diagonal offset is proposed row is 2. The old row is 0. So 2 minus 0 is 2. So the diagonal offset is at 0, 1, 2. As you can see, that's the diagonal. So it just works. It's pretty ingenious. And so we have the diagonal offset check is 2. The old column is 0. Old row is 0. And so we check if the old column is the same with the proposed column, yeah, then they're lined up. Like in this case, right? We know that that's not a safe bet. And so we say, oh, it's an invalid move, return false, it's not valid. If it's if it's equal to the old column is equal to the proposed column negative the diagonal offset. So for example, if it is in this axis, right, that's what the minus does, then that's not good either. The plus checks if it's in this axis. Okay, so if, for instance, something was here, right, then this condition would have stopped it, would have caused its valid function to return false. And if we're evaluating this and something was somewhere over here, right, then this positive diagonal offset would have triggered. This case would have triggered. This last case would have triggered and returned false. Now that we're done checking if a move is valid, we'll call a recursive function called solve n queens recursion, or REC for recursion, to place the queens on the chessboard. I will start by placing the queen in the first column of the first row. For every placement, we'll check if a move is valid. If yes, we add it to our solution. And let's run this. It has a lot of console logs, but super useful stuff. So we have solve queens recursive, and we're calling it in here, right? After we've generated an array of -1 solutions for columns, possible columns, then we pass in n our current solutions. What is 0? Check. Okay, the current row we're evaluating, which is the first row, and then the results array that we want to populate. So this is what we're defining now, and you see that it's here that we call the is valid that we just looked at, And we're not done creating this, but you'll see what is going on. So remember, we have the same generating the board so far. So far we've not created any solutions yet. So -1 for -1 all things. As you can see, so that's what's done here in the solve queens functions. That's what's logging everything so far. It printed the board, as you can see. Now we're placing queens. And under placing queens, we are gonna look at this. So we place queen 1 in row 0 and check if the move is valid. Yes, it is a valid move. The proposed cell is safe because nothing is going to attack us, and we've looked at is valid already. That's what this check is. So it's valid. We're gonna add it to the solution this way. So solution index at that particular row, we said it's an I that we're evaluating right now, and we're done. That's all there is to this recursive call for now. Stay tuned. So for each row, once our queen is placed at the correct position, we recursively check if another queen can be safely placed in the next row. If it can, we add it to the position to our solution and move to the next queen. Otherwise, we backtrack to the previous valid solution and try a different configuration. If we successfully reach the last row of the chessboard, we save that solution to the results array and backtrack to find alternatives. So I'm gonna run this real quick. So some changes have been made to this same solve n queens recursive. Some important changes. For one, they added a check. So if we eventually get to the last row, then we found a valid solution. So we're gonna push, we're finally using this results variable, push a solution in there, right? And be done with it. Otherwise, and this is something I wish they highlighted, quite frankly, they call the function again. So in this loop that's looping through n, values of n, for every valid thing we find, we have to move on to the next thing. So we have to call it again, but increment the row, check the next row for the solve queens function, and it's going to call itself again, and it only terminates when either when the row is equal to n, or fails to call again when it's not valid, basically. So there's a lot of console logs in here, but the cleaner solution is going to be available in the GitHub link below, and I'll probably just show it before we're done here. But as you can see, it starts with queen 1 in row 0, queen 2 in row 1, and you remember the diagram we looked through. That's not going to work, so it backtracks and starts again, basically, and that's what's playing out here. And I believe we have gone through everything. Yep, that is all. Sorry, I scrolled down about that. And this is the solution, the complete solution, without all the comments. This is what it looks like. Well, I mean, this is what it looks like in one view. I think this shows a lot more per screen. So our isValid function, what it does without all the console logs, and our recursive solve queens function, right, that's only called if it's valid, right? It only goes into the call stack, the recursion if it's valid, and we increment the row past the same results, the same solution, the same n. And this is our initial function that starts it, kicks it all off, essentially. So yeah, code in the description. Boy, this is a lot. This is one of the longer videos I've made lately. Recurrence relation for the solution is this fancy schmancy mathy stuff, but eventually evaluates to this n factorial, which is still, I mean, it works, right? It's better than the n to the power 2, right? N to the power 2n that we were getting before. So, and then the space complexity is O of n, where n is the dimension of the chessboard, because the maximum number of calls to the recursive worker function is n, 1 for each row, and each call takes up O of 1 space on the call stack. Then the next one is the iterative solution. So I'm getting tired, but we're almost there. Perhaps this should have been 2 videos. Maybe I would just chop it up into 2 videos, but I don't think that's necessary. This problem is hard, right? It's hard. Any way you want to look at it, it's hard. So it's worth reviewing again and again till it sticks. And how to explain. So there's an iterative form where you use a stack to keep track of the current solution. And many iterative versions of recursive solutions end up doing this, using a stack to kind of take abstract the call stack for the recursion that you were doing prior. But sometimes it tends to be less elegant and bigger, like lots of more code to deal with. So the stack only holds the column values, and one solution is stored in the stack at a time. When one solution is complete, we have the solution present in the stack we save it, the solution present in the stack, to a separate list of valid solutions. We then backtrack by popping from the stack and resuming the search for the next solution. And this diagram is instructive. So we have the stack. We start off the same way we started off down here. Then we check 2. Then we realize, oh, 2 ain't gonna work. So we pop it and push 3. Right. Then we push like so. Oh, that's not gonna work. That's not gonna work. And then move down here and we keep going till we're done. And then we backtrack again till we can find another valid move and just keep going like so. So, I mean, quite intuitive, I have to say. And this is what that looks like in code. We have the same is valid function. This doesn't change between the recursive and the iterative solution. So you remember that. That's what this is. Well commented. And then we have the solve endpoints. So, and it's not recursive. So this is all there is to that. And you can see it's quite a lot, actually. And we can step through it line by line. Time is short, but yeah, let's go through it. We have results, we have the solution that we're evaluating, we have the solution stack. We start off with row 0 and column 0. So while the row is less than n, so while that's the terminating condition. And then while the column is less than n, we check the first one if it's valid. And if it's valid, what do? We add the solution stack to the solution to the stack. We increment the current solution similar to what we did last time. We increment the row, check the next row, and start again from column 0 and break. But if not, we'll just check the next column and keep going. And then if we checked all the columns and the solution stack, it had something valid in it, we take it out. So this is where backtracking is happening. This is a lot, but worth looking into. So that should be it for me for now, quite frankly. Do you want to go recursive? Do you want to go iterative? It depends entirely on you. The iterative solution seems more elegant, right? Can even put them side by side. It's just, yeah, way more elegant, like so fewer lines of code, just this and this, and you're done. So I'm leaning towards this, I have to say. But if I had to debug and stuff, then this guy is your friend, really, pretty much, at times. So yeah, I'll call it quits here. See you in the next one. Oh, before I go, have I discussed time complexity? I believe it's the same time complexity either way, right? And factorial, same space complexity. So, I mean, pick your poison, right? See you in the next video.